Hi, and welcome back to Codex. Our speaker today is Naoki Sato, who is a professor in the math department at UC Davis and director of the UC Davis Tetrapods Institute of Data Science. Professor Sato is a world expert in applied harmonic analysis, specializing in graph signal processing and boundary value problems for elliptic PDEs. We are very pleased to welcome him here today to tell us about his latest work on multi-scale graph basis dictionaries. Please take it away, Naoki.
Okay, thank you very much, Joey, for your nice introduction. And thank you very much for inviting me for this Codex seminar. So when I wrote my abstract, I was a little bit too ambitious. So I was trying to basically talk about all the multi-scale graph basis dictionaries we worked on for the last 8 years, but it was too difficult to do that within 1 hour or 15 minutes. So therefore, I reduced this to the two basic graph basis dictionaries we developed, which basically serves the purpose, in fact. So here's the outline of my talk today. The first, I would like to give you some motivations, and then I will review some important aspect of classical multi-scale basis dictionaries, which basically like wavelet packets and then local cosine transforms. And then we discuss briefly the basics of graph theory language. Then I'm going to talk about two main dictionaries of bases we have developed so far. Okay, so there are two different aspects which basically serve as a kind of dual, okay, to each other. So finally, I'm going to give you some small numerical examples, and then I will conclude with my summary and then some softwares and so forth. Okay. So first, before talking about anything, so I just would like to acknowledge my support, like NSF grants and ONR grants, and my collaborators, Jeff Ilion, Ikun Shao, and Hauten Lee, were all my PhD students, former PhD students. And Alex Grolinger is my collaborator at UC San Diego. Okay, so what I wanted to do for a long time was to lift and then transfer classical multi-scale basis dictionaries to the graph setting. Right? So for conventional digital signals and images sampled on the regular lattices, multi-scale basis dictionaries, which include wavelet packet dictionaries, which of course include also in turn wavelet basis or wavelet transform, and local cosine dictionaries, right? Okay, so those guys have proven track record of success, like JPEG 2000 image compression standard and modified discrete cosine transform in MP3 compression, and then discriminant feature extraction for signal classification and what have you, right? So we wanted to lift those so useful tools to the graph setting, and of course we are not the only group, right? Other people have been also doing this, but we have some specific viewpoints on this construction, or lifting those classical tools to modern tools or graph setting. And for example, we want to move, lift Shannon wavelet on real axis or interval to something like a graph situation like figure B for graph signal processing and graph data analysis. Okay, so I'm not going to talk about too much realistic applications today because I don't have enough time to talk about the details of interesting applications so much. So rather than that, my today's talk is about how to overcome the difficulties we faced, okay, when we try to lift classical tools to graph setting. Okay, so let's review a little bit about classical multi-scale basis dictionaries. Okay, so classical multi-scale dictionary, basis dictionaries, including wavelet packets and local cosine transforms and so forth, basically depends on the so-called rigid hierarchical bipartitioning. So initial space, let's say, sampled signal with endpoints, right? Okay, and n in the classical setting, as if you worked on these wavelets and wavelet packets and the digital implementation, often this number of points should be dyadic number, 2 to some number, J max in this case, okay? Then you can get nice fast algorithm based on FFT and then filtering and so forth, okay, right? Convolution filters and so forth. And then what happens is that original space, let's say omega, okay, which is Rn, right? Okay, endpoint signal, okay, space of endpoint signal is split into two pieces, omega 1, 0 and omega 1, 1. Okay, so interesting thing is that when you split this original space into two pieces, okay, and then you do something, okay, then omega 1, 0, omega 1, 1 again is split into two pieces. Okay, of course, big question is what to split and then where how you split these. Okay, and then you split hierarchically, and then I'm only showing this one at the level 3, right? So you have 8 smaller pieces. So here's a corresponding table. Okay, so this is very useful to know. So hierarchical block DCT, okay, is using hard partitioning. So you brutally chop the input signal into two pieces in the middle, okay, and then you do the DCT on both sides. Okay, and then again you split the first half into two pieces, okay, and the lower later part into two pieces, okay, brutally, okay, sharply, okay, and then you do the discrete cosine transform on those little intervals, small short intervals, and so forth, and then you repeat, right? Okay, local cosine transform is partition is not brutal or not hard. Okay, it does overlapping soft partitioning. Okay, but idea is the same in the sense that you partition the original domain, time domain or space domain, into 2 pieces, 4 pieces, and 8 pieces, and so forth, right? Okay. Now, Hall-Walsh wavelet packet is something, it's very interesting. And then I wanted to talk about this also in the graph setting, but I don't have enough time to talk about it. And then you can basically check some of my publications on my website about this. Okay, so I will skip this one. Okay, so now wavelet packet is, in some sense, you can view as a dual of local cosines and discrete hierarchical block discrete cosine transform. What you are going to do here is that you partition the not the original time domain or space domain of the data or signal, but you partition the frequency domain. So you partition the frequency domain into 2 pieces, either a hard way, which basically lead to the so-called Shannon wavelet packets, or in a nicer way with overlap or soft partition, which basically lead to compactly supported wavelet packets. Okay, so essentially this one, you partition the frequency information into 2 pieces, low frequency, high frequency, and then each frequency band again is split into 2 pieces, like a low frequency, high frequency, low frequency, high frequency, and so forth. So you do it hierarchically. Okay, so that's basically the idea of classical dictionary. Of course, there are a lot of details, but I'm not going to talk about details. The basic idea is important here. So just a little bit more notations. So each little piece, okay, regardless of space, time domain, or frequency domain, let's say omega jk, jth level at the case subspace, is the number of points or dimension is n over 2 to the j. J equals 0 is the root original space, right? Okay. So that we call NJ. And then each portion, subspace omega jk, we have set of orthonormal bases phi jkl. And L goes to NJ to minus 1, right? Okay. So these are number of orthonormal vectors in hierarchical bipartition tree, which is n times 1 plus log 2n. That's the number of basis vectors you have. First level is n. The next level is, of course, n. Okay, and then you have 1 plus log 2n levels, okay, of the depths of the tree. Okay, if you basically develop full hierarchical bipartition tree. So the number of orthonormal basis vectors, are just n times basically log n. But okay, one can choose immense number of orthonormal bases from this tree structured subspaces or tree structured basis vectors. It contains more than 1.5 to the power n, okay, possible orthonormal bases. Okay, this number 1.5 to the power n is a huge number, because if n is 1000, right, 24 and so forth, it basically gets to a very large number, of course, right? Or maybe n is 10,000, it gets huge. Okay, so this possible number of orthonormal bases basically comes from various discrete math algorithm, like the oldest one, Flageolet or Odryzko in 1984. Okay, they talk about the depths of binary trees and so forth, and then it turns out that the number of basis choosable orthonormal bases from this hierarchical bipartition tree, okay, let's say Bj is the number of choosable bases, then this Bj plus 1 is equal to Bj squared plus 1. Okay, and then B0 is 1, and then you start this recursion, and then you can get this asymptotic number, all that 1.5n, okay, which also discussed by Thiele-Villemot in 1996. Okay, so then what you do with this large number of bases, right? Okay, so possible bases. Then we typically use Koifman-Wickerhauser best basis algorithm or its variant. Okay, and then we can choose these orthonormal basis, which is most suitable for your task, like a compression or nice efficient approximation. If that's the case, then maybe we want to use a sparsity or L1 norm minimization of the expansion coefficients, okay, and then smallest L1 norm minimization basis coefficient, okay, is chosen. That basis is called best basis, for example. But then you can tune this optimization criterion, not necessarily minimizing L1 norm, but also other functionals, okay, cost functionals like Kalbach-Leibler divergence or Wasserstein distance between those distribution of signal coefficients and so forth under the this dictionary. So a lot of work basically for the classical multi-scale based dictionaries were done earlier. So now what we want to do, okay, is, okay, so all these classical dictionaries, the original space, or what space we want to partition is the following, summarized in this table, right? Okay, so hierarchical block DCT, local cosine transform dictionaries, partition original space, or time axis, or time domain, or space domain. Okay, Harosh, okay, it's interesting, but I'm not going to talk about. Okay, and then compactly supported wavelet packets and Shannon wavelet packets, we partition in the frequency domain. Those are the classical world. Okay, so the graph world, we have all these, abbreviation. I'm going to talk about those abbreviations next page. But the HGLET, hierarchical graph Laplacian eigentransform, which corresponds to hierarchical block DCT. So that one, okay, the domain to partition is a primary graph or input graph, G. Okay, we partition the graph. Okay, and then corresponding version, LPHDRET corresponds to local cosine transform using smooth partitions. That one I also do not talk about today, unfortunately. Okay, is partition original graph. Okay, input graph G. Okay, in the contrast, okay, so compact tree supported wavelet packets. Okay, Shannon wavelet packets. We partitioned frequency domain in the classical case. So then, in the graph world, what domain we should do partition? So that's a question I'm going to talk about later on today. Okay, that's a dual domain of the graph. What is the dual domain of the graph? Okay, so that's a very interesting and important question I'm going to discuss later on today. So basically, the underlying philosophy or so-called basso continuo, okay, of the whole dictionary, multi-scale based dictionary ideas is essentially split, organize, merge. Okay? So you split some domain or information or data into pieces, and then each piece after split, you do something like organization, reorganization, or manipulation, or filtering, or whatever you want, right? Okay, and then finally you merge, okay, those local information into some more coherent, interesting information you want to search or you want to use. Okay, so that philosophy is very important and useful in many different contexts. Okay, split, organize, merge. Okay, so a little bit of history. I don't want to spend too much time here, but a hierarchical block cosine transform history, it's not entirely clear to me. Of course, we know that block discrete cosine transform is used in JPEG, old JPEG, classical JPEG standard DCT, DCT, right? Okay, but that was basically fixed level of the tree, like 8x8 blocks. Okay, it's not hierarchical. So hierarchical version of block discrete cosine transform, I'm not really sure who basically discussed first. So if you know any historical information about this, please let me know. And the local cosine transform was, initially, there are a lot of course, earlier history, but actually, Marva, Stalin, Marva, and Koihman and Meyer essentially developed local cosine transform of this, of the current form, which is late 80s, early 90s. And Haber-Bosch wavelet packet was done by Koifman, Meyer in 1989. And extended version, which is very interesting. Okay, it basically gives you much larger dictionary than original dictionary of Haber-Bosch, is done by T. Villemot in 96. Compactly supported wavelet packets also, when I basically checked the history, Koihman and Meyer wrote this very interesting preprints, Yale preprints in 1990. It's so that was the beginning of this thing. Then Shannon wavelet packet, again, it's not entirely clear who basically this. So Shannon wavelet was, of course, already discussed by Ingrid Dobeshi's book of 10 lectures. But wavelet packet version, it's not clear to me who basically started talking about this. So now the graph world case, we have this hierarchical graph Laplacian eigentransform by me and Jeff Ilion, my former graduate student, and so forth. So these are more recent, of course. Okay, and then the last one, natural graph wavelet packets, I'm going to also talk about. These red ones are main subject of today's talk. Okay. All right, so graph basics, I'm going to go through very quickly about this. So here we have a graph, okay? So graph nodes are V1, V2, and so forth, like if you have n nodes, okay, are connected, okay? At each node represents some, something, some some object, okay? Maybe a sensor or maybe a person. And then you measure some information, okay, at this node. And then you also measure the relationship between those nodes, okay, which is if these nodes are connected by edges, okay. So now we have, in order to describe this graph topology and then this information about between those nodes, we need so-called edge weight matrix W. Okay, so Wij is edge weight between I and j's node. Okay, so like this figure. All right, so typically, if we have an unweighted graph, okay, which means that only the connection between the nodes are of your interest, okay, not necessarily, okay, how these two nodes are related, okay, how these two are close or different, right, similar or different. Rather than that, if you are only interested in the topology or how these guys are connected, then you use unweighted graphs, and then this weighted graph is just a 0-1 matrix. If it's connected directly or adjacent, okay, ij's node are adjacent, then 1, otherwise 0, right? Okay. So on the other hand, weighted graph, basically you can encode some information measured at i's node and j's node, okay. And then typically, this is important, right? Wij should indicate affinity or similarity between I and j, not necessarily the distance or the similarity between this. So therefore, if you have a distance measure, some kind of measure of the similarity between information available at i's node and j's node, which dist ij, then we should use inverse of this distance, okay, as a edge weight. And distance, okay, you can think about all sorts of different things, like Euclidean distance between spatial location, if you have a coordinate, like, or Wasserstein distance between some vector value measurement between recorded ij location, or the exponential version with the scale parameters, like Gaussian weight, right? Okay, typical one. All right, so now our assumption here is that we only think about finite graphs. Okay, and then also undirected, and I assume every graph we talk about is connected, and then simple. Okay, simple means that there's no self loop and multiple edges. Okay, of course, then very, very interesting direction, okay, of research is, okay, what to do with directed graph, for example, okay, which I'm going to briefly mention in the last slide. Okay, so now, okay, let's talk about a matrix called graph Laplacians. Okay, graph Laplacian essentially is the discretized version of second order differential operator, okay, or Laplacian on the graph. Okay, okay, negative Laplacian actually, right? Okay, so this consists L of G. Okay, given graph G, Laplacian matrix of G is defined as degree matrix minus this weight matrix. Degree matrix is the sum of all weights of that connected to ith node. Okay, so ith entry of this degree matrix is just a sum of the weights, okay, connected to the ith node. Okay, because this matrix is L is symmetric and non-negative definite, so eigenvectors form an orthonormal basis, and then those eigen values, okay, can be ordered from a smallest one, which is 0, okay, and then largest one is lambda n minus 1. We use this notation. We start index from 0 to n minus 1. Then corresponding eigenvector is phi 0, phi 1, and so forth. Okay, so so therefore these vectors phi 0, phi 1, and phi n minus 1 form an orthonormal basis of Rn, and then in particular, but because of assumption that all these graphs we talk about are connected, so the phi 0 is constant vector. It's called DC vector. Phi 1, next one, is a Fiedler vector, which is very important, okay, to use partitioning. Okay, and then we have other version of Laplacian matrices, like a random walk normalized Laplacian, okay, which is LRW, which we often use for partitioning the graph. Okay, or we have a symmetric version. Okay, so this is a very simple but important example. This is a path graph Pn. Okay, Pn is a path, okay, like this figure, okay, consisting of n nodes, and the edge weight are all one. Okay, so then this Laplacian matrix LOG, okay, is this tri-diagonal matrix, okay, 1 minus 1 minus 1 2 minus 1 so forth. So okay, only those first row and second last row basically is different, and all the other portion is just second order different scheme, right? Okay, so this one, okay, we know that eigenvalue is lambda L is 4 times sine squared pi L over 2n. Okay, and then also eigenvectors, basically we know explicitly. It turns out that this is the same as a discrete cosine, exactly the same as DCT type 2, which was used in JPEG standard. Okay, it's very interesting that that was the case. I was very surprised when I first noticed this one in a long time ago, like 2009 or 2008. This is exactly the same. Okay, so it's in some sense it's a magic, right? Okay, so so then the problem is that, okay, in this simple case, okay, if you look at this lambda lambda L, it's 4 times sine squared pi L. So sine is a monotonically increasing as a function of this frequency L. So therefore, this lambda L, okay, you can view as a square of frequency. Okay, in this simple case. Okay, however, if your graph becomes more complicated than this one, then you basically may encounter some problems. Okay, so I'm going to talk about that one too in a minute. Okay, so now finally, okay, let's start working on the first dictionary, multi-scale graph basis dictionary, which we do, which we apply hierarchical partitioning on a primal domain, which is an input graph G. Okay, so first I'm going to talk about graph cut problem. Okay, partitioning with by spectral clustering. So there are a lot of work on the spectral clustering, so I do not want to spend too much time on this one. Okay, so the basically we need to cut the input graph into nicely 2 pieces, and in order to do that, okay, we need to find the weakest link or weakest edge to partition. At the same time, you want to maintain that after the partition, the size of the graph, subgraph, okay, more or less the same, because you don't want to cut the graph like there are huge guys one, and then there's only small one, okay, and then you don't want to cut in an unbalanced manner. So it's better to partition the graph into more or less organized and roughly equal sizes. So in order to do that, okay, so one typical and very popular idea is to use the so-called Fiedler vector I mentioned, right? Okay, of random walk weighted graph Laplacian matrix. Okay, so essentially this phi 1, if you compute phi 1, okay, so then there's a positive component, a negative component of this eigenvector, Fiedler vector. So non-negative component, okay, and then corresponding node, okay, and then negative portion, okay, you split depending on the sign of the phi 1, we split into 2 pieces, okay. So this one, okay, using this way, okay, it Shi and Malik in 2000 very famous paper, okay, discussed that this based on the Fiedler vector of this random walk weighted Laplacian, essentially approximately solve the minimization problem, so-called normalized cut. Okay, so this is a cut metric, okay, divided by volume of A. Volume of A is sum of the all weights on the set A. Okay, A and AC is mutually exclusive, and if the union exactly the same as original vertices, nodes V, right? Okay. So this one, okay, is trying to cut the minimum, weakest link, and then trying to balance these two partitions after this. So we typically use this, okay, for hierarchical partitioning, okay. But I have to basically mention that our graph basis dictionaries is, you can use any other clustering or graph cut method, not necessarily tied to this Fedora vector-based method. Okay, if you provide those partitions, okay, hierarchical partitions, we can construct our multi-scale graph basis dictionaries. But in this talk, we basically use Fedora vector of random walk graph Laplacian. Okay. All right. So now here's just a typical hierarchical diagram, like original graph or original node VG. I denote it by V00, right? And V00 is split into two pieces, V10, V11, so forth. Okay, and then you keep doing this. Okay, and then you keep doing this until you reach to actually the bottom is only single node remains. Okay, each node basically each leaf contains only one node. Okay, so we basically do this until we reach to the bottom. Okay, so let's move on to, because you can see these details of this conditions. Okay, so here's a diagram of P applied to P6. Okay, so if you have a 6-node path graph, this is split into two pieces, like a 3-3 node. Okay, now the next level, okay, this 3-node, okay, you cannot partition into 2-2 and so forth, right? So that's the difficult. Okay, okay. So in the classical case, we only use dyadic number, so this doesn't happen. But in the graph case, we need to think about this one. But by thinking about this graph version, actually, we can apply graph-based algorithm to the classical signal, images, okay, whose size is non-dyadic. So that's very also useful too. Okay, here, okay, so sorry for the deviation. So now, if you split into two pieces, like a three nodes, okay, then 3-node piece, okay, is split into two pieces, like a 2-1, okay, nodes, right? Okay, and then this 2-node case, okay, 2-node situation is split again into two pieces. And if you reach to one area, okay, then bottom, then you just transfer this, like no partition. Okay, that's what we are going to do. Okay, so in the end, we basically have only one node, okay, at the bottom level or leaf. Okay, so here's a more realistic graph. Okay, this is a Toronto street network. I'm going to talk about this graph a little bit later. Well, this is just an illustration. So this is a partition using a Fedora vector into two pieces. So it's based. So this is these edges. The node, these nodes basically corresponds to intersection of the street of the city of Toronto. Okay, and then edges corresponding to the actually road, right? Okay, or street. So this one, okay, using this Fedora vector, it's split around here, which is reasonable, right? Okay, and then level 2, so that is into split into 4 pieces, like here, 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 right? Okay, using different colors. And the level 3, again, that portion is partitioned into 2, so you have 8 regions now. All right, so now this HGRED, okay, hierarchical graph Laplacian eigentransform is very, very simple idea. Yet we got the best paper prize from Japan Siam in 2016. So that was nice. The idea is very simple. Once you basically obtain hierarchical bipartition tree of the input graph, right? Okay. Then for at each subspace, okay, each subgraph GJK, or in the case of node, it's VJK, right? Okay. We just compute eigenvectors, okay, of graph Laplacian of that subgraph, okay, and then we keep doing this, okay. So so that's it, okay. So therefore, in the case of input graph is path graph, right? Okay, and then you split into pieces. Then each piece basically becomes a block discrete cosine transform. Okay, you exactly so if the input graph G is a path graph, then it exactly reduces the classical case of block hierarchical DCT. Right? Okay. And then if the n is a dialectic number, then you can of course use faster computation thanks to FFT. So therefore, computational cost is order n log 2 n squared for this tree. But in general case, in the graph case, it takes order n cubed because mainly due to the eigenvector computations. And then how to reduce this order n cubed is of course the main concern, but I'm going to talk about some of the ideas in the last. Okay. So of course you can construct the same thing or same structure of the basis dictionary using eigenvectors of symmetric version graph Laplacian or weighted version random walk version also. So here's some of the basis functions I computed. Okay, so amplitude is coded in two ways, like a color and also the size of those nodes corresponding to a larger absolute magnitude, absolute amplitude of the base of the vector. So therefore these small ones look like a zero, right? Okay, tiny, okay, in terms of amplitude, near from zero, or maybe some of them are zero. Okay, little dots basically is a small amplitude. Okay, so this guy basically have large positive amplitude eigenfunctions around here. This is a level 0. This is a global eigenvector, right, of graph Laplacian. So it's oscillating. It's like a cosine, right? Okay, of frequency 5. Okay, you are basically oscillating in this direction mainly. Okay. So this is phi 1101. So this is scale level 1, which is only this lower left portion because this split into two pieces, right? Okay, and then this portion, okay, is eigenvectors are computed, and then this is a 0, 1, right? Okay, so around here, okay, 0 corresponding to a region or location information, and then next 1 here basically is indicate the eigenvalue index, right? Okay, so it's trying to actually, this one is Fiedler vector of this region 1, okay, around here. So it's trying to, next one, okay, it should split into two pieces like around here, actually. So this is level 2, and the frequency index or eigenvalue index is a little bit larger, like 5. So therefore it's oscillating, you can see a little bit more. But concentrating on this, city region or really, downtown region. This is even more, right? Okay. So, and this is even more. This is a very, localized. Okay, only around here, right? Okay. So this is level 10. Okay. So now, okay, I'm going to talk about some of applications. Okay, later on in a numerical example. Let's move on to the next one, which is how to partition the dual domain or some so-called frequency domain in some sense, okay, of the graph. Okay, so that is useful or important in order to construct smooth wavelet packet basis on the graph. Okay, before, okay, like HGLET, you brutally partition the original graph into pieces. So therefore, all these are basis vectors in this dictionary. at least, okay, if the region is, doesn't, have any intersection, okay, even its neighboring ones, like, okay, the basis vectors are not, smoothly overlap between them, okay, because it support of eigen basis vectors in HGRED, okay, is strictly on those partitioned set of nodes, right? Okay, here, okay, it's because we are trying to do a frequency domain partition in some sense, or dual domain partition, okay, basis function, there's no split in the original domain, okay, or to a primary domain, okay. So that's interesting because that then give you more smooth basis vectors or smooth localized basis vectors in the original domain, okay, by doing partitioning on a dual domain. Okay, so now the big question is, what is a dual domain of a graph? Okay, so we want to build a graph wavelet packet that are smooth in primary domain, which is on on input graph domain. And we already talked about this, but classical setting, the dual domain of input signal is well defined. Okay, it's a reciprocal regular lattice representing a Fourier mode. Okay, using a discrete Fourier transform. If you can see this, right? Okay, original domain like a lattice, 1D lattice or 2D lattice. You do the Fourier transform, and then this becomes Fourier grid, right? Okay, so but in the graph setting, it's very difficult to do the same. Okay. In the graph setting, using graph Laplacian eigenvectors as a cosines or Fourier mode on graphs with eigenvalues as a square of their frequencies, okay, has been popular. But this viewpoint is strictly speaking only true for path graph or simple cycle case. Okay, cycle case, okay, eigenvectors of graph Laplacian becomes complex, exponentials like a sines and cosines. Okay, and in the case of PN, this becomes a DCT. Right. So the notion of frequency on a general graph is ill-defined. Because we also worked on also interesting things like extremely localized eigenvectors and phase transitions and things like that sort. So it's not a simple global sinusoid with different frequencies anymore. Okay? It strongly depends on the topology of the graph. Okay, even if the input graph is slightly more complicated than path graph, in fact, the 2D lattice case I'm going to talk about, okay, it's already picture or situation becomes completely different. So therefore, one of the point here is that, okay, eigenvalues, we cannot really view eigenvalues as simple function of frequency, like a frequency squared, right? Okay, unless the graph is path or simple path or cycle. Okay, so here's the situation. So if you do even 2D, we can see the problem. Okay, if you do 2D lattice graph like PM times PN, okay, let's say it's a rectangular domain and you sample this rectangular strip, okay, into n points in x direction, n points in y direction, and let's say m is larger than n. Okay, then Laplacian eigenpairs we know explicitly using a 1D case. Okay, case eigenvalue is a sum of 1D eigenvalues. Okay, like a 4 times sine squared pi kx to m plus sine squared pi ky over 2m, right? Okay, and then case eigenvectors corresponds to the product of cosines or eigenvectors of x direction or y direction. Okay, it looks okay like this is great, right? Okay, we know this. Okay, but the problem is that suppose you don't know the formula, okay, of this. Okay, and then you just do input this, this graph to the and then graph Laplacian matrix to the eigenvalue solver. Then all you get is a sequence of lambda k's and phi k's, right? Okay, that's the only thing you know. Unfortunately, so therefore, for each k, okay, you don't know what kx and ky ki's are. Okay, nobody tells you this frequency in x direction or y direction. All the eigenvalue solver give you is a sequence of eigenvalues and eigenvectors ordered in a one-dimensional way. But this has a degree 2 freedom, right? Okay, x direction, y direction. So this is a problem. And then actually this leads to some analytical number theory questions. It's very interesting, but I'm not going to talk, I cannot talk about this one today. So if you compute this eigenvectors of a very simple P7 times P3, okay, 7 points times 3 points. This rectangular, 2D lattice, and then I compute eigenvectors, and then it basically, I order this one in terms of increasing, in terms of eigenvalues. This phi 0 corresponding to eigenvalue 0, phi 1 is the next eigenvector corresponding to the Fiedler vector, okay, and so forth, right? Okay, so then what you can see here is that the oscillation increasing in horizontal direction first, but then look at this one, phi 3, okay, all of a sudden, okay, so oscillation in x direction stops, and then you have a one oscillation in y direction, right? Okay, and the phi 4 is now oscillation in y direction 1, right? One oscillation, and then one oscillation in x direction. But now phi 5, okay, suddenly oscillation along y direction stops, and then have a more high frequency oscillations in x direction and so forth. So I'm trying to demonstrate that if you order eigenvectors in terms of increasing eigenvalues, okay, you are ignoring the properties or behavior of eigenvectors. So that basically means that we cannot really organize, okay, the eigenvectors simply by looking at the eigenvalues. Okay, we need to investigate and check the behavior of eigenvectors themselves. Okay, so that's a difficulty. Okay, so what we want to do is, instead of ordering these eigenvectors in terms of increasing eigenvalue order like this in the bottom half, what we want to do have a more meaningful organization, right? Okay, here I organize these 21 eigenvectors into the following form, right? Following order. So his horizontal direction, right? Increasing the x frequency in x direction. Vertical direction, so frequency in y increasing. So we have only 3 columns, 3 points along y. So therefore only no oscillation, 1 oscillation, 2 oscillation. Right? So phi 6, 2, this is the highest oscillation both in x and y. Right? So if you can organize like this way, right? Okay, then you can partition this. You can start grouping those eigenvectors into, right, like a low frequency, high frequency, and so forth in a classical, similar to classical way, right? Okay, so then you can build something like a localized wavelet that behaves well. But if you try to organize in the eigenvalues in terms of if you try to organize eigenvectors in terms of increasing eigenvectors, okay, so you are mixing basically apples and oranges. Okay, so so how can we then measure the behavioral difference between given two eigenvectors? So this is an interesting question, because L2 norm or L2 distance doesn't work, okay, between orthonormal eigenvectors, because orthonormal basis vectors, because phi I minus phi j of L2 norm is always square root of 2, right? Okay, if I and j are different, okay, so you cannot see any difference between two orthonormal vectors, okay. So therefore we need to do something else, okay, and then we choose a metric, okay, some distance between phi and phi j, okay, and then we compute the distance matrix between phi and phi j, and then encode this distance among this i's vector and j's vector eigenvector, and then compute this distance matrix, and then we can construct a dual graph Okay, so the dual graph here is essentially each node is corresponding to eigenvectors. So ith node corresponding to phi I, and then edge weight. Okay, edge basically is connected to phi I and phi j. Okay, is affinity between these two eigenvectors. Okay, which is inverse of entry over distance matrix I computed, or you can use Gaussian distance, right? Okay. So then once you construct this dual graph, which is typically fully connected, okay, depending on how you define distance, right? Okay, but you can organize and then partition this dual graph or dual nodes of dual graph, which is eigenvectors of the original graph, right? Okay, and then you can generate wavelet packet vectors on the graph. Okay, so I don't have enough time to talk about various different metrics, and then we propose and then various different ones, including ramified optimal transport distance, and then Kroninger and Steinerberger also developed average of local correlations of eigenvectors and so forth. And here, okay, you can take a look at some of our papers if you are interested in the details of these. But one of the simple one, which we used in this talk, is the difference of absolute gradient. So this one essentially is you compute the gradient or derivative of an eigenvector. Okay, so Q is an incidence matrix. Okay, you need to set up, for each edge. Okay, you need to set up even undirected. You need to artificially specify which is head, which is tail, so that you have 1 and -1 for each column of this Q, which shows the edges, okay, which node connects to the which node. So you have m edges, right? Okay, so this is so-called incidence matrix, and the incidence matrix transpose times phi gives you the a difference, okay, of the eigenvectors components, okay, and then you take the absolute value. Okay, this one basically gives you roughness of the eigenvectors, local roughness, more or less absolute value of derivative, really, right? Okay, and then you can show that this distance, okay, DAG distance squared is related to the Kroninger Steinerberger Adamar product-based affinity, but I don't have enough time to talk about the details here. So if I use that, okay, distance, okay, DAG distance, okay, and then compute the dual graph of this P7 times P3, okay, and then the distance matrix is computed, right? Okay, so then if I use classical multidimensional scaling to just visualize how these eigenvectors or nodes on dual graph is organized, so you can take a look at this, right? Okay, this is in some sense a little bit rotated and skewed version of what I wanted to, right? Okay, so this one corresponding to basis vectors, eigenvectors increasing a frequency, a horizontal frequency, okay, but no oscillations in y. Right? This guy is one oscillation in y direction, and then all this along this way, oscillation in x direction is increasing. Right? This is the highest frequency in y direction, and then again organized frequency is increasing in horizontal direction along this way. So I'm very happy, okay, by, we can basically compute the dual domain like this, or dual graph like this. Of course, okay, this P7 times P3 is just a toy example, but I just wanted, and we know absolutely, what's going to happen. Therefore, this is really a toy example, but and then nobody is really, need to do this for P7 by P3, right? But I just wanted to show you what's going to happen in this simple case. All right, so now finally, this natural graph wavelet packet. So once we construct this dual graph G star, okay, we recursively bipartition, okay, this G star using any method, but typically we use again Fiedler vectors of G star, and then after that we again compute small dual graph, okay, and then compute their Fiedler vectors to partition further, okay, and then after partitioning this, which means that we are grouping, okay, equivalently we are grouping similar eigenvectors as a group, right? Okay, and then we do something. We need to do a localization of this, localized eigenvectors. So that's a second step. Okay, so this we call natural graph wavelet packet. Okay, and then there are some other possibilities, some various possibilities in step 2 how to localize. Okay, but I'm going to talk about only one method. Okay, so details were published as a part of the topical collection, Harmonic Analysis on Combinatorial Graphs, okay, of the Journal of Fourier Analysis and Applications earlier this year. So you can take a look at it. So essentially, this eigenvector matrix, original eigenvector, Graph-Laplacian eigenvector matrix, we call phi 0, 0, is grouped, partitioned into 2 groups, 4 groups, hierarchically like that. Okay, so if I apply, okay, first of all, hierarchical partition on this dual graph, okay, of this simple TOEIC example case, okay, so because this is an odd number in both sides, 7 and 3, right? Okay, so you need to do some partition first, okay? So this Fiedler vector-based partition on the dual graph of this P7 and P3, okay, the partition into 2 pieces using this red line. Okay, it's split into these 2 pieces. The next level, okay, it's split into 4 pieces like that. Okay, like this portion, this portion, this portion, this portion. That's basically computed using Fiedler vector, and then partition is done automatically. So now, yes.
I'm sorry to interrupt. We're running low on time, so
yeah,
we can take about 4 more minutes and then maybe.
All right. So now these pieces, after partition, we need to do some localization of those eigenvectors, because those eigenvectors may be more oscillatory and global nature, right? Okay. So in order to do that, we decided to use so-called Varimax rotation, okay, on this each piece. Okay, so that Varimax rotation is orthogonal rotation, often using factor analysis, and then trying to maximize the scale version of kurtosis, and then trying to make the vectors, input vectors, more peaky or spiky, or more localized. So again, I'm not going to talk about the details, but it basically trying to maximize the fourth order moments, okay? And then we can do this orthogonal rotation numerically, okay? And then once you do that, we can generate Shannon wavelet packets in the case of path graph. This is a further wavelet, like sinc functions. Okay, this is a mother wavelet. Okay, and this is a more high frequency wavelet packet vectors, Shannon wavelet packets computed using this our algorithm. Okay, and then in the case of this P7 by P3, okay, after these partitions, if we do this Varimax rotation, all these eigenvectors basically becomes more localized, and then becomes like a wavelet, like a localized vectors like this, right? Okay. And then this is more like a second derivative, localized second derivative operator here, okay? And then this is a scaling function and the translation and so forth, okay? So that's the idea. So let's go through some of the examples, and then that's it, okay? Maybe I'm just going through. Let's skip this example, because it's more important to talk. We can compute all these basis vectors, okay, and then this is an approximation experiment using all sorts of different dictionary, okay, for the given data. Like this is pedestrian counts on the street. It's very localized and so forth. And then you can compute these eigenvectors again, okay, and then choose the better ones. Okay, and then let me skip this one too, and then I'm going to summary here. Okay, so summary is the following. So we lifted the classical multiscale basis dictionaries like hierarchical block DCT and Shannon wavelet packets to graph setting, right? Which we call HGRET and NGWPs respectively. Okay, and then if the input graph is path graph, okay, then HGRET and NGWP exactly reduce to the HBDCT and the Shannon wavelet packet respectively. So this is a, this gives us peace of mind, right? Okay, and then using a hierarchical bipartitioning of a primal graph, then we get the HGRET. And then if you do the same thing in a dual graph, G star, then we get NGWP. Okay, but then in the case of dual graph, we need to be careful using how to basically compute the distance between dual graph nodes, which are eigenvectors of original graph. Okay, and then we use Varimax rotation. So graph signal approximation experiments, I didn't have enough time to talk about it, but we have this demonstrated the advantage of data adaptive basis dictionaries, which tune to the smoothness and locality of the input data. And these graph-based dictionaries also can be used for classical signals and images, especially if input signal is size is not a non-dyadic shape, non-dyadic length. Then you know classically, okay, you need to do all sorts of trick like reflection at the boundary or zero padding and all sorts of things. But here, using graph-based method, you don't have to do that, right? Okay. And then also another important thing to mention is that we are separating the geometry and statistics of data. Okay, PCA-based basis always incorporate the statistics of data into the basis. In our case, basis vectors and the dictionaries are independent from the data observed over there. It basically depends on the geometry of the structure of the measuring, lattice graph. Okay, so future plan. This is the last one. So, how can we reduce the computational complexity of order n cube is a big question if we want to make them practical. Right. Okay. So for certain problems, of course, one may not need all the graph Laplacian eigenvectors. In particular, those corresponding to the large eigenvalues, you may not need them. So that you can reduce the computation. But more interestingly, if you think about something like a green functions or integral operators instead of differential operator like a graph Laplacian, then it may be possible to use something like a fast multipole method. And then for non-graph situation, like a Euclidean domain situation, I already proposed this one. And the Sue wrote a PhD dissertation based on that idea, not graph, but also just a regular domain, irregular domain shape object. So we also need to truly generalize local cosine transform for graph setting. And then my another PhD student recently, Haoten Lee, recently constructed a graph version of a smooth orthogonal projectors involving orthogonal folding and unfolding operators. And then constructed wrapped version of HGRET and NGWP. But to be more effective, we need to use different boundary conditions in order to compute eigenvectors of graph Laplacian. Right now, graph Laplacian eigenvectors are computed using usual Neumann boundary conditions, but we need to tune this boundary condition a little bit in order to be fully effective, and then construct a true cosine local cosine transform on the graph. All right, so then we need to explore some different cost functions other than sparsity, of course, like a local discriminant basis and local regression basis, so forth for the input set of input graph signals, okay, not a single signal. And finally, I just would like to mention that how can we generalize graph basis dictionaries to directed graphs, higher order networks, and hypergraphs. That are very, very interesting. And then Hodge Laplacian, of structure, okay, we are looking at right now. Now, for higher order networks and hypergraphs and so forth, you have also the information not only at the node, but also on the edges, okay, on the triangles, okay, and so forth, right? So we need to do more, okay, in order to compute, analyze those data, not necessarily, measured only at the nodes, but also on the edges and the triangles and so forth, right? Okay, so in order to do that, we need Hodge Laplacians. Okay, and that's it. So you can see my publication. This is some of them on my website. Okay, and then I would like to mention that we coded all these algorithms in Julia, a programming language, and then you can visit this website. Again, the idea is split, organize, and merge. Okay, with all these classical ones and then more graph-based ones. Okay, thank you very much for your attention.
Thank you. And we can all click on the bottom where it says reactions. And we can all thank our speaker. And we don't have much time, but we have maybe just